In the preceding section, we used the sign of the derivative of f prime to determine where a function was increasing and where it was decreasing. In this section, we will use the sign of the second derivative f prime prime to determine where the derivative is increasing and where it is decreasing. This approach utilizes the geometric property of the graph of the function f known as concavity. Concavity is essentially the way the graph curves. It can be either concave up or down. Here we see a curve that is concave up, meaning if this was like a bowl shape, it faces up and things would stay in it. Here's concave down, things would fall out, it is downward facing, while this is upward facing. Here we can see more concavity. It is concave down from here to here, but then switches to up here, back to down, and then back to up again. Graphs can have many different concavities all at the same time. The rules for determining concavity are as follows. A graph is concave up if the second derivative f prime prime of x is positive, and concave down if the second derivative f prime prime of x is negative. The first step in finding the concavity and using this to graph the function is essentially to take the first derivative. So we will do this with this problem here. Next, we just simply take the second derivative, f prime prime of x, finding that it is 6x plus 2. And then we can factor this to make it easier on us, and factor out a 2, leaving 3x plus 1. We must next find the zeros, or the critical points. Here we can see that there is only one critical point, x equals negative 1/3. We must then plot that critical point on our number line as we did in the first derivative test. We then plug in numbers on either side of it, below it and above it to determine whether it is concave up or down. Picking a number greater than 1/3, let's say 0, we find that it is positive, and picking a number less than, let's say negative 1, we find that it is negative. Now we can graph this. Once again, we must graph our critical point, negative 1/3. From the earlier section, in which we used the same equation, we saw that the critical points from the first derivative were 1 and negative 5/3. And that the graph was rising, falling, and then once again rising. Using this, we know that the graph was rising until about negative 5/3, and then falling, all the while concave down. However, at negative 1/3, the graph switches to being concave up, and then at 1, from rising to falling, or from falling to rising. So we can determine that the graph switches concavity at negative 1/3 with the patterns that we determined from the first derivative test. Where the graph switches from negative to positive, the graph of the second derivative switches from negative to positive is called an inflection point, and these occur when f is continuous and there is a point C where f prime prime switches from positive to negative or negative to positive at that C. For example, at this point here, it goes from being concave down to concave up. The derivative goes from second derivative goes from negative to positive, making this an inflection point. It is also continuous through the point. We can also use the second derivative test to find extrema. F prime prime of C, if it's less than 0, then is a maximum, because the second derivative is negative and is therefore concave down. If the second derivative is positive, f is a minimum at C, as it is concave up, therefore minimum.